So now we're going to start talking about moments and centers of mass, moments of inertia, and whatever else. And so it's probably best to take a little trip down memory lane and recall that from Calc 2 that the mass of an object you get by integrating from A to B the density of that object, and then the moment, the x moment of that object. I guess we're thinking about like a rod or something like that. That's usually the kind of thing they talk about. This looks like the same integral, except now we've got x thrown in there as well. So it looks something like this. And then we can talk about the center of mass of this thing. And it's going to be the x-coordinate given by mx divided by mass. And so we already saw this actually in probability. So in probability, this one is equal to 1. And so this one here would just be called the mean and denoted by mu, the Greek letter m. Okay, so now let's generalize this to, well actually no, before we talk about higher dimensions, let's just talk about the meaning of what's going on here. This is best understood, I think, in terms of torques. So if we have, so here's our little bar balance beam, and say this is 0, and then we've got like 1, and then da 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 da, all the way up down to the end. This is 10 and 9 and 8. And I've got masses hanging. So here's each of these has like 1 unit of mass. So I'm putting little ones in them, which makes them look like eyeballs. Eyeballs hanging from a stick. Well, that's lovely. Anyways, so now the question is, we want to figure out where to put our little fulcrum balance beam so that this thing will balance, right? And so if we compute the center of mass of this setup as the integral from a to b x times density dx, in this case it's actually just going to end up being a sum because it's a discrete model of it. So we're going to be summing up the position xi times the density at xi, which is just going to be the weight that I've put there. And so let's see, so we've got one at 1 and it weighs 1, and we've got one at 8 and it weighs 1, and we've got one at 9 and it weighs 1, and we've got one at 10 and it weighs 1, and we add this all up and we get 28, and the total mass is clearly equal to 4. So our magic x coordinate is 28 over 4, which is 7. And so in fact, if we take our little fulcrum and move it over here so that it's resting right here at 7, then this apparatus, ignoring the then this apparatus will balance. Okay, and so one thing I want you to notice here is that the mean is not the median. In other words, it does not divide the mass in half. Notice that the mass on one side is, the mass on one side is 1 and the mass on the other side is 3. So the masses on opposite sides are not the same. The median is the thing that finds where the masses on either side are the same, and the median would be any point in between 8 and 9. For the mean, it matters how far you are. So for instance, over here, we've got a distance of 6. So the torque is actually going to be 6 times 1. On the other side over here, we've got a torque of 1 times 3, and a torque of 2 times 3, and a torque of 1 times, I said that wrong, 3 times 1 and 2 times 1 and 1 times 1. and you add 3 plus 2 plus 1 and you get 6, and those torques balance. Okay. All right, okay, so that's our walk down memory lane complete. Let's go on to doing this for a solid object in R3. Now we're going to be talking about the mass distribution on either side of a plane. So here's a plane, and we want to figure out where to put the plane so that the sum of the masses times the torque, or times the distance going this way for all of these masses in our object, so here's our object, is equal to the distance times the mass at that distance, distance times mass at that distance, blah, 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 of all the parts of the object on the other side. That's a horrible picture. I don't even know. It looks like a diseased Chernobyl broccoli or something. Sorry about that. Okay, so the way that we denote this is that if this is the plane y equals some constant, then we're going to be looking at the mxz moment to figure out what y coordinate to put that one. And that would be triple integral over e of y, the coordinate we want to determine, times the density d volume. And similarly, we also have myz in order to get the x moment. And mxy, the z moment. All right, and just as before, we have the y mean and the x mean and the z mean. And in case you're wondering why I did y first instead of x, it's just because I thought it would be nicer to draw this picture, but that was before my picture came out so ugly. So then the center of mass is the coordinate, or is the place with coordinates x mean, y mean, z mean. So that's how we find the center of mass.